Assalamualaikum warahmatullahi wabarakatuh. First, I would like to introduce myself. My name is Arunaditya with NIM 210101191302120. And this is my presentation on why, what, how, and interoperability. First, the table of contents. We have four things to discuss. The first one is why, number two is what, number three is how, and number four is interoperability. First one, why? Why is BIM? In the last decade, digitalization has transformed a wide range of industrial sectors, resulting in a tremendous increase in productivity, product quality, and product variety. In the architecture, engineering, construction industry, or AEC, digital tools are increasingly adopted for designing, constructing, and operating buildings and infrastructure assets. However, the continuous use of digital information along the entire process chain falls significantly behind other industry domains. All too often, valuable information is lost because information is still predominantly handed over in the form of drawings, either as a physical printed plot on paper or in a digital but limited format. Such disruption in information flow occur across the entire lifecycle of built facility in its design, construction, and operation phases, as well as in the very important handover between these phases. The planning and realization of built facilities is a complex undertaking involving a wide range of stakeholders from different fields of expertise. For a successful construction project, a continuous reconciliation and intense exchange of information among these stakeholders is necessary. Currently, this typically involves the handover of technical drawings of the construction project in a graphical manner in the form of horizontal and vertical sections, views, and detailed drawings. The software used to create these drawings imitate the centuries-old way of working using a drawing board. However, line drawing cannot be comprehensively understood by computers. The information they contain can only be partially interpreted and processed by computational methods. Basing the information flow on drawings alone therefore fails to harness the great potential of information technology for supporting project management and building operation. A key problem is that the consistency of the diverse technical drawings can only be checked manually. This is a potentially massive source of errors, particularly if we take into account that the drawings are typically created by experts from different design disciplines and across multiple companies. Design changes are particularly challenging if they are not continuously tracked and relate to all related plans. Inconsistency can easily arise and often remain undiscovered until the actual construction, where they can incur significant extra costs for ad hoc solution on site. In conventional practice, design changes are marked only by means of revision clouds in the drawings, which can be hard to detect and ambiguous. The limited information depth of technical drawings also has a significant drawback in that information on that building design cannot be directly used by downstream applications for any kind of analysis, calculations, and simulation, but must be re-entered manually, which again requires unnecessary additional work and is a further source of errors. The same holds true for the information handover to the building owner after the construction is finished. He must invest considerable effort into extracting the required information for operating the building from the drawings and documents and enter it into a facility management system. At each of these information exchange points, data that was once available in digital form is lost and has to be laboriously recreated. This is the graphical information about information loss between digital workflow and conventional workflow. Loss of information caused by disruption in the digital information flow. And it's divided into four sections. First one, conceptual design, detailed design, construction, and operation. Each has its own information loss based on the project information in its time. This is where building information modeling comes into play. By applying the BIM method as a much more profound use of computer technology in the design, engineering, construction, and operation of built facilities is realized. Instead of recording information in drawings, BIM stores, maintains, and exchanges information using incomprehensive digital representation. the building information models. This approach dramatically improves the coordination of the design activities, the integration of simulation, the setup and control of the construction process, as well as the handover of building information to the operator. By reducing the manual re-entering of data to a minimum and enabling the consequent reuse of digital information, laborious and error-prone work is avoided, which in turn results in an increase in productivity and quality in construction projects. Other industry sectors, such as the automotive industry, have already undergone the transition to digitized model-based product development and manufacturing, which allowed them to achieve significant efficiency gain. The architecture, engineering, and construction industry, however, has its own particularly challenging boundary conditions. First and foremost, the process and value creation chain is not controlled by one company, but is dispersed across a large number of enterprises, including architectural offices, engineering consultancies, and construction firms. These typically cooperate only for the duration of an individual construction project and not for a longer period of time. Consequently, there are a large number of interfaces in the network of companies where digital information has to be handed over. As these information flows must be supervised and controlled by a central instance, the responsibility is on the building owner to specify and enforce the use of building information modeling. Number 2, what? According to the US National Building Information Modeling Standard, defines BIM as follows. Building Information Modeling, or BIM, is a digital representation of physical and functional characteristics of a facility. A BIM is a BIM is a shared knowledge resource for information about a facility, forming a reliable basis for decisions during its life cycle. Defined as existing from earliest conception to demolition. A basic premise of BIM is collaboration by different stakeholders at different phases of the life cycle of a facility to insert, extract, update, or modify information in the BIMs to support and reflect the roles of that stakeholder. This is an example of BIM models in picture. A BIM model comprises both the 3D geometry of each building element as well as rich set of semantic information provided by attributes and relationship. For example, this is a picture of a building with its many attributes and relationships such as the column, the curtain wall, door, object, opening, slab, space, stair, and wall. The concept of building information modeling relies on the continuous use and low-loss handover of digital information across the entire lifecycle of built facility. First, we have conceptual design with this spatial program, design options, visualization. Second, we have detailed design, coordination, cost estimation, simulation and analysis, drawing derivation, quantity takeoff, and tendering. Next part, we have construction with its prefabrication, process simulation, progress monitoring, logistic, building. Next up, we have operation with its facility management, maintenance, repair, and lastly, we have modification, recycling, retrofitting, and it's a cycle that goes on and on and on. A building information model characterizes the geometry, spatial relationships, spatial relationships, geographic information, quantities and properties of building elements, cost estimates, material inventories, and project schedule. The model can be used to demonstrate the entire building life cycle. As a result, quantities and shared properties of materials can be readily extracted. Scopes of work can be easily isolated and defined. Systems, assemblies, and sequences can be shown in a relative scale with the entire facility or group of facilities. The construction documents such as the drawings, procurement details, submittal processes, and other specifications can be easily interrelated. BIM can can be viewed as a virtual process that encompasses all aspects, disciplines, and systems of a facility within a single virtual model, allowing all design team members such as owner, architects, engineer, contractors, subcontractors, and suppliers to collaborate more accurately and efficiently than using traditional processes. As the model is being created, team members are constantly refining and adjusting their portions according to project specifications and design changes to ensure the model is as accurate as possible before the project physically breaks ground. A building information model can be used for the following purposes. 1. Visualization. 3D renderings can be easily generated in-house with little additional effort. Number 2, fabrication or shop drawings. It is easy to generate shop drawings for various building systems. For example, the sheet metal ductwork shop drawings can be quickly produced once the model is complete. Third, code reviews. Fire department and other officials may use these models for the review of building projects. Fourth, cost estimating. A BIM software has built-in cost estimating features. Material quantities are automatically extracted and updated when any changes are made in the model. Fifth, construction sequencing. A building information model can be effectively used to coordinate material ordering, fabrication, and delivery schedules for all building components. Sixth, conflict, interference, and collision detection. Because building information models are created to scale in 3D space, all major systems can be instantly and automatically checked for interference. For example, this process can verify the piping does not intersect with steel beams, ducts, or walls. 7. Forensic analysis. A building information A building information model can be easily adapted to graphically illustrate potential failures, leaks, evacuation plans, and so forth. And lastly, facilities management. Facilities management department can use it for renovation, space planning, and maintenance operation. To define of what constitutes BIM technology is subject to variation and confusion. To deal with this confusion, it is useful to describe modeling solutions that do not utilize BIM design technology. These include tools that create the following kind of models. Models that contain 3D data only and no or few object attributes. These are models that can only be used for graphic visualization and have no intelligence at the object level. They are fine for visualization, but provide little or no support for data integration and design analysis. Models with no support of behavior. These are models that define objects but cannot adjust their positioning or proportion because they do not utilize parametric intelligence. Models that are composed of multiple 2D CAD reference files that must be combined to define the building. It is impossible to ensure that the resulting 3D model will be visible, consistent, countable, and display intelligence with respect to the objects contained within it. Lastly, models that allow changes to the dimensions in one view that are not automatically reflected in other views. On to the next question. What are the benefits of BIM? BIM technology and associated processes can help to respond to the increasing pressure on a building over its life cycle. With increased pressure on the building processes, we use BIM analysis tools, IPD, Lean, and we got reduced time for design and construction, reduced costs for design and construction, sustainable design and construction, increased complexity of design, reduced costs for energy use, improved building performance, and reduced construction costs and time. We have different type of benefits to every stakeholder. First one, pre-construction. We have different type of benefits with each phases to each stakeholders, and Here we have pre-construction benefits to owner. First, concept, feasibility, and design benefits. Before owner engage an architect, it is necessary to determine whether a building of a given size, quality level, and desired program requirements can be built within a given cost and time budget. In other words, can a given building meet the financial requirement of an owner? If these questions can be answered with relative certainty, owners can then proceed with the expectation that their goals are achievable. Finding out that a particular design is significantly over budget after a considerable amount of time and effort has been expended is wasteful. An approximate or macro building built into and linked to a cost database can be tremendous value and assistance to an owner. Secondly, we have increased building performance and quality. Developing a schematic model prior to generating a detailed building model allows for a more careful evaluation of the proposed scheme to determine whether it meets the building's functional and sustainable requirements. Early evaluation of design alternatives using analysis simulation tools increase the overall quality of the building. Lastly, we have improved collaboration using integrated project delivery. When the owner uses integrated project delivery or IPD for project procurement, BIM can be used by the project team from the beginning of the design to improve their understanding of project requirements and to extract cost estimates as the design is developed. This allows design and cost to be better understood, also avoids the use of paper exchange and its associated delays. Next one, we have design benefits. Number one, we have earlier and more accurate visualization of a design. The 3D model generated by the BIM software is designed directly rather than being generated from multiple 2D views. It can be used to visualize the design at any stage of the process with the expectation that it will be dimensionally consistent in every view. Number two, we have automatic low-level correction when changes are made to the design. If the object used in the design and are controlled by parametric rules that ensure proper alignment, then the 3D model will be free of geometry, alignment, and spatial coordination errors. This reduces the user's need to manage design changes. Number three, we have generation of accurate and consistent 2D drawings at any stage of the design. Accurate and consistent drawing can be extracted for any set of objects or specified views of the project. This significantly reduces the amount of time and number of errors associated with generating construction drawings for all design disciplines. When changes to the design are required, fully consistent drawing can be generated as soon as the design modifications are entered. We have number four, earlier collaboration of multiple design disciplines. BIM technology facilitates simultaneous work by multiple design disciplines. While collaboration with drawings is also possible, it is inherently more difficult and time-consuming than working with one or more coordinated 3D models in which change control can be well managed. This shortened the design time and significantly reduced design errors and commission. It also gives earlier insight into design problems and presents opportunities for a design to be continuously improved. This is much more cost-effective than waiting until design is nearly complete, then applying value engineering only after the major design decisions have been made. Number five, we have easy verification of consistency to the design intent. BIM provides earlier 3D visualization and quantifies the area of space and other material quantities, allowing for earlier and more accurate cost estimates. For technical buildings such as labs, hospitals, and the like, The design intent is often defined quantitatively, and this allows a building model to be used to check for this requirement. For qualitative requirement, this space should be near another. The 3D model also can support automatic evaluation. Next, we have extraction of cost estimates during the design stage. At any stage of the design, BIM technology can extract an accurate bill of quantities and spaces that can be used for cost estimation. In the early stages of design, cost estimates are based either on formulas that are key to significant project quantities, for example, number of parking spaces, square feet of office areas, and of various types, or unit cost per square foot. As the design progresses, more detailed quantities are available and can be used for more accurate and detailed cost estimates. It is possible to keep all parties aware of the cost implication associated with a given design before it progresses to the level of detailing required of construction bid. At the final stage of design, an estimate based on the quantities for all the objects contained within the model allows for the preparation of more accurate final cost estimate. Next one, we have improvement of energy efficiency and sustainability. Linking the building model to energy analysis tools which allows evaluation of energy use during the early design phases. This is not practical using traditional 2D tools because of the time required to prepare the relevant input. If applied at all, energy analysis is performed at the end of the 2D design process as a check of regulatory requirement, thus reducing the opportunities for modification that could improve the building's energy performance. The capability to link the building model to various types of analysis tools provides many opportunities to improve building quality. Next up, we have construction and fabrication benefits. Use of design model as basis for fabricated components. If the design model is transferred to a BIM fabrication tool and detailed to the level of fabrication object or shop model, it will contain an accurate representation of the building objects for fabrication and construction. Because components are already defined in 3D, automated fabrication using numerical control machinery is facilitated. Such automation is standard practice today in steel fabrication and some sheet metal work. It has been used successfully in precast components, fenestration, and glass fabrication. This allows vendors worldwide to elaborate on the model, to develop details needed for fabrication, and to maintain links that reflect the design intent. This facilitates off-site fabrication and reduces cost and construction time. The accuracy of BIM also allows larger components of the design to be fabricated off-site than would normally be attempted using 2D drawings due to the likely need for on-site changes or rework and the inability to predict exact dimensions until other items are constructed in the field. It also allows smaller installation crews, faster installation time, and less on-site storage space. Next, we have quick reaction to design changes. The impact of suggested design change can be entered into the building model, and changes to the other objects the design will automatically update. Some updates will be made automatically based on the established parametric rules. Additional cross-system updates can be checked and updated visually or through clash detection. The consequences of change can be accurately reflected in the model and subsequent views of it. In addition, the design changes can be resolved more quickly in a BIM system because modification can be shared, visualized, estimated, and resolved without the use of time-consuming paper transaction. Updating in this manner is extremely error-prone in paper-based system. Next, we have discovery of design errors and omissions before construction. Because the virtual 3D building model is the source for all 2D and 3D drawings, design errors caused by inconsistent 2D drawings are eliminated. In addition, because models from all disciplines can be brought together and compared, multi-system interfaces are easily checked both systematically for hard inclusions clashes and visually for other kind of errors. Conflicts in constructability problems are identified before they are detected in the field. Coordination among participating designers and contractors is enhanced and errors of omission are significantly reduced. This speeds the construction process, reduce costs, minimize the likelihood of legal dispute, and provide a smoother process for the entire project team. Next up, we have synchronization of the design and construction planning. Construction planning using 4D CAD requires linking a construction plan to the 3D objects in the design so that it is possible to simulate the construction process and show what the building and site would look like at any point in time. This graphic simulation provides considerable insight into how the building will be constructed day by day and reveals sources of potential problems, opportunities for possible improvement, site, crew, and equipment, space conflicts, safety problems, and so forth. This type of analysis is not available from paper bid documents. It does, however, provide added benefit if the model includes temporary construction objects such as shoring, scaffolding, cranes, and other major equipment so that these objects can be linked to scheduled activities and reflected in the desired construction plan. Next, we have better implementation of lean construction techniques. Lean construction techniques require careful coordination between the general contractors and all subs to ensure that work can be performed when the appropriate resources are available on site. This minimizes wasted effort and reduces the need for on-site material inventories. Because BIM provides an accurate model of the design and the material resources required for each segment of work, it provides the basis for improved planning and scheduling of subcontractors and help to ensure just-in-time arrival of people, equipment, and material. This reduces costs and allows for better collaboration at the job site. The model can also be used with wireless handheld computers to facilitate material tracking, installation progress, and automated positioning in the field. This benefits. Lastly, we have synchronization of procurement with design and construction. The complete building model provides accurate quantities for all or most depending upon the level of 3D building of the material objects contained within a design. These quantities, specification, and properties can be used to procure material from product vendors and subcontractors such as precast concrete subs. At the present time, the object definition for many manufactured products have not yet been developed to make this capability a complete reality. However, when the models have been available, steel member, precast concrete members, some mechanical components, some windows and doors, the result have been very beneficial. And next we have post-construction benefits. First, we have improved commissioning and handover of facility information. During the construction process, the general contractor and MEP contractors collect information about installed materials and maintenance information for the systems in the building. This information can be linked to the object in the building model and then thus be available for handover to the owner for use in their facility management systems. It also can be used to check that all the systems are working as designed before the building is accepted by the owner. Next, we have better management of operation of facilities. The building model provides a source of information, graphics, and specification for all systems used in a building. Previous analysis used to determine mechanical equipment, control system, and other purchases can be provided to the owner as a mean for verifying the design decisions once the building in use. This information can be used to check that all systems work properly after the building is completed. And lastly, we have integration of facility operation and management systems. A building model that has been updated with all changes made during construction provides an accurate source of information about the as-built spaces and systems and provide a useful starting point for managing and operating the building. The building information model supports monitoring of real-time control systems, provide a natural interface for sensors and remote operating management of facilities. Many of these capabilities have not yet been developed, but BIM provides an ideal platform for their deployment. Next, what challenges can be expected? First one, we have challenges with collaboration and teaming. While BIM offers new methods for collaboration, it introduces other issues with respect to the development of effective teams. Determining the methods that will be used to permit adequate sharing of model information by members of the project team is a significant issue. If the architect uses traditional paper-based drawings, then it will be necessary for the contractor or a third party to build the model so that it can be used for construction planning, estimating, and coordination. If the architect does create their design using BIM, the model and coordination, the model and co if the architect does create the design using BIM, the model may not have sufficient detail for use for construction or may have object definitions that are inadequate for extracting necessary construction quantities. This may require creating a new model for construction use. If the architectural model is provided, cost and time may be added to project, but the cost of model is usually justified by the advantages of using it for construction planning and detailed design by mechanical, plumbing, other subs and fabricators. Design change, resolution, procurement, and so forth. If the members of the project team use different modeling tools, then tools for moving the models from one environment to another or combining these models are needed. This can add complexity and introduce potential errors and time to the project. Such problems may be reduced by using IFC standard. For exchanging data, another approach is to use a model server that communicates with all BIM applications through IFC or proprietary standards. These capabilities. Next up, we have legal changes to documentation, ownership, and production. Legal concerns are presenting challenges with respect to who owns the multiple design, fabrication, analysis, and construction datasets, who pays for them, and who is responsible for their accuracy. These issues are being addressed by practitioners through BIM use on projects. As owners learn more about their advantages of BIM, they will likely require a building model to support operation, maintenance, and subsequent renovation. Professional groups such as the AIA and AGC are developing guidelines for contractual language to cover the issues raised by the use of BIM technology. Next up, we have changes in practice and use of information. The use of BIM will also encourage the integration of construction knowledge earlier in the design process. Integrated design build firms capable of coordinating all phases of the design and incorporating construction knowledge from the outset will benefit the most. IPD contracting arrangement that require and facilitate good collaboration will provide greater advantage to owner when BIM is used. The most significant change that companies face when implementing BIM technology is intensively using a shared building model during design phases and a coordinated set of building models during the construction and fabrication as the basis of all work processes and for collaboration. This transformation will require time and education, as is true of all significant changes in technology and work processes. Lastly, we have implementation issues. Replacing a 2D or a 3D CAD environment with a building model system involves far more than acquiring software, training, and upgrading hardware. Effective use of BIM requires that changes be made to almost every aspect of firm's business, not just doing the same thing in a new way. It requires some understanding of BIM technology and related processes and plan for implementation before the conversion can begin. A consultant can be very helpful to plan, monitor, and assist in this process, while the specific while the specific changes for each firm will depend for their sectors of AEC activity. The general steps that need to be considered are similar and include the third, third one we have how. The shift from conventional drawing-based workflows to model-based one requires significant changes in both internal company workflows as well as cross-company processes. To avoid unduly unsettling the basic functioning of established workflows, a stepwise transition is recommended. Accordingly, different technological levels of BIM implementation are distinguished. The simple differentiation is expressed by the terms big beam and little beam. Here, little beam describes the application of a specific BIM software by an individual stakeholder to realize a discipline-specific design task. Typically, software is used to create a building model and derive the drawings, which are then fed into the conventional process. The building model is not used across different software packages and is not handed over to other stakeholders. This BIM implementation is therefore an insular solution within one design discipline, with all external communication taking place using drawings. Although implementing Little BIM can offer efficiency gains, the big potential of comprehensively using digital building information remains untapped. By contrast, Big BIM involves consistently model-based communication between all stakeholders and across the entire life cycle of a facility. For the data exchange and the coordination of the model-based workflows, digital technologies such as model servers, databases, or project platforms are employed in a comprehensive manner. Alongside the extent of BIM usage is the question of whether software products from just one vendor are employed, closed BIM, or whether open vendor neutral data formats are utilized to allow to be exchanged between products by different software vendors, open BIM. Although some software companies on the market provide a large range of software products required for the design, construction, and operation of built facilities, there will always be a need to exchange data with other products that either serve a specific purpose or are used by other stakeholders in the overall process. The variety of software system in use is usually a product of the many disciplines involved and the distribution of tasks across different companies. The term little beam and big beam describe the extent of beam usage. The terms closed beam and open beam distinguish between the exclusive use of software products from a single vendor and the use of open vendor neutral data exchange format. Here we can see we have four different beams: little open beam, big open beam, big closed beam, and little closed beam. All depends on the extent of BIM usage and the exclusivity of the software product. The construction industry cannot realize the big transition to fully digitized model-based working procedures i.e. big open beam in one go. Instead, a more appropriate approach is to introduce the new technology and the accompanying changes in processes step by step. To illustrate this, the UK BIM task group developed the BIM maturity model, which defines four discrete levels of BIM implementation. One, we have level 0, level 1, level 2, level 3. Level 0 describes conventional working practice based on 2D CAD and the exchange of paper-based drawings. Level 1 comprises the partial 3D modeling of the facility, mostly for complex geometries, while most of the design is still realized by means of 2D drawings. Here, the data exchange is realized through sending and receiving individual files and a central project platform is not employed. Level 2 is defined by the use of BIM software products for authoring digital building models. However, each of the various disciplines involved develops its own model. Their mutual consistency is ensured by periodic coordination sessions, where the individual submodels are brought together and checked for clashes or other discrepancies. Data exchange is still realized on the basis of files in native format. However, all files are managed on a central platform called a Common Data Environment, or CDE. Level 3, which is targeted for the future, is based on the concept of a fully integrated BIM. It is based on the implementation of big open BIM, i.e. ISO standards are employed for data exchange and process description, and deeply integrated digital models are used throughout the entire life cycle. The introduction of BIM brings with it numerous new tasks and responsibilities for the management and coordination of digital building models. This means not only that there are new roles in the project team, but also new professions. The most important roles are that of the BIM manager, the BIM coordinator, and the BIM modeler. Currently, there are no broadly agreed description of these roles. Most guidelines accord the BIM manager a strategic role in the company, responsible for guiding the transition toward digital practices and for developing guidelines regarding workflows, model contents, and best practices. The BIM coordinator, by contrast, is a role assigned on a per project basis and is responsible for coordinating the specialist discipline, merging submodels, checking model contents, and applying quality control in order to meet the client's demands. The modeler is an engineer or architect responsible for developing the model. Lastly, we have interoperability. In the BIM world, the word interoperability is often used. Multiple applications with overlapping data requirements supports various tasks of design and construction. Interoperability is a characteristic of a product or system whose interfaces are completely understood to work with other products or system present or future in either implementation or access without any restriction. With respect to software, the term interoperability is used to describe the capability of different programs to exchange data via a common set of exchange formats, to read and write the same file formats, and to use the same protocols, in which smooths workflows and sometimes facilitates their automation. Interoperability has traditionally relied on file-based exchange format limited to geometry, such as DXF or Drawing Exchange Format, and IGES, or Initial Graphic Exchange Specification. Direct links based on the application programming interfaces, or APIs, are the oldest and still important route to interoperability. Starting in the late 1980s, data models were developed to support product, and object model exchanges within different industries led by the ISO STEP International Standards effort. Data models distinguish the schema used to organize the data and the schema language to carry the data. Some translators can be from one schema language to another, for example, from IFC to XML. These are the common exchange formats in AEC application. First, we have image formats such as GPG, JPG, GIF, TIF, BMP, PNG, RAW or RAW, and RLE. Next up, we have 2D vector formats such as DXF, DWG, AI, CGM, EMF, IGS, WMF, BGN, PDF, ODF, SVG, and SWF. Third, we have 3D surface and shape formats such as 3ds, WRL, STL, IGS, SAT, DXF, the DWG, OBJ, DGN, U3D, PDF, PTS, DWF, so on and so forth. Architecture, engineering, and construction all need to have access to interoperable systems for BIM to work. These are the main players that create the models together with many other stakeholders in the process who have to rely on this information, project managers, clients, etc. So each organization will need to be able to access the same information and use it with their relevant tools. Here are some critical points for interoperability in BIM and AEC. First up, we have planning or construction phase. The planners in the AEC industries use an exclusive format for model creation. This proprietary approach allows those who have access to the same software to work together and access the same information. Next up, we have operation and renovation. Interoperability is not only necessary during the start of a project, but it may also be needed many years down the line. If a building needs any renovation or remodels, for example, then all AEC individuals involved will need to access the same information and work with it. Using open file schemes like IFC guarantee that you can use your models and data along the entire life cycle of a building. Interoperability plays a major role in integrating future software that we are not yet sure of. The AEC field is learning what kind of information is needed for different tasks, what is important for effective workflows, and how to document the required information. Second, it has learned that most applications rely on fixed or non-editable geometry, and only a few need to create or edit geometry data. We are learning that interoperability in most cases can be made straightforward. Various XML schemas are being used for a growing number of businesses and some analysis exchanges, and these are also expanding into design type exchanges. We expect to see these changes grow, especially for incremental updates. The need for explicit exchange standards is becoming recognized, and such standards will become used in the definition of project scale business practices. The BIM platform developers will continue to offer packaged solutions, while reliance on the IFC will grow to provide workflows not well supported by the software vendors, while reliance on the IFC will grow to provide workflows not well supported by the software vendors. The trend to IFC will hopefully grow as robust MVDs are defined and implemented. In parallel, the need to gain help managing heterogeneous data from diverse platforms in complex projects is increasingly recognized as a major productivity problem. BIM servers are becoming a new market with BIM servers, different exchanges, whether proprietary through an open standards or manual, become steps in the workflow for the project. All approaches are expected to coexist with different mapping being adopted as small technology increments. That's all for the presentation on why, what, how, and interoperability for BIM. Thank you so much for your attention. Assalamualaikum warahmatullahi wabarakatuh.